So let's continue the conversation about conservation of momentum. In order to do that, we're going to use these carts and this track. These carts are the same mass, different colors but the same mass. And they have a little spring for the one of them. And they glide with, a relatively little friction. So we can try to take friction out of the picture. So what I'm going to do is I'm going to make the red one here. I'm going to try to have it be at rest. I'm going to bring the blue one in from the side, and I'm going to have them collide. Now, we're going to consider this an elastic collision, meaning we don't really lose any energy. We're going to try not to because of the use of the spring. We're going to kind of ignore friction, or try to. And what I'll notice, if they're exactly the same mass, if I bring the one cart in from the side at a speed, a velocity, the other one takes off, and this one tries to come to a stop. Momentum must be conserved. If the blue cart has mv coming in, it hits the red cart. And if the blue cart stops, that means the red cart must have the same speed after the collision that the blue cart had before the collision, because if they're the same mass, the mv before the collision from the blue car, momentum before the collision, has to be equal to the momentum, the m times v, of the red car after the collision. I hope that's evident. Now I can, of course, well, let's show that once more. Pretty clear. Now what I can do is alter their masses. I can take a heavier object and put it into one of the cars. And so what I'm going to do is I'm going to take the heavy object, I'm going to make blue, the blue car, the heavier object. So now we have m times v with the blue car. We're going to smash it into the red car. And we'll notice not only does the red car take off with a decent speed, because you had a good amount of momentum coming in for the blue car, that means the momenta, plural momentum, of the red car and the blue car after the collision have to equal whatever was given from the blue car in the beginning. Let's just make up a number. Let's say the momentum of the blue car was 10 kilogram meters per second before it hit. So after the collision, the momentum of these guys together must add to 10. And in this case, you did see the blue car continue moving just a little bit after the collision. It has a little bit of motion, so maybe this has a momentum of 1. That means this has to have a momentum of 9, because 1 plus 9 has to equal 10 of the blue car before they collide. Now, if we take the heavy object and put it on the red car, let's again say the blue car comes in with a momentum of 10 kilogram meter per second. Again, I'm just making up a number. You'll notice that the blue car actually goes backwards a little bit. Well, that's significant because that's a negative momentum. Remember, if the momentum before the collision was 10, the momentum after the collision has to also add to 10. But here's the problem. This is going to be a negative momentum because it's going in the negative direction. So maybe this has a negative momentum of 2. Well, if that happens, that has a negative momentum of 2, but that and that got to add to 10. Then this has to have a forward momentum of 12. So that can happen depending on the scenario. And again, all of these cases, we're going to assume that energy was not lost significantly because of the spring system. And again, that's called elastic collisions. So when energy is not lost, it's elastic collisions. Now, of course, we can have the objects come at each other, and if we have equal but opposites momenta coming at each other, then they of course should bounce off with the same momentum. So if I bring them in roughly at the same speed, they should bounce off each other with the same speed, roughly. Now, obviously, if I have different speeds for each different cart, then you're going to have to calculate what the speeds are after the fact. But here's the thing. When I have these two carts coming at each other like this, assuming the same speed, that's not quite the same speed, but we'll try again. If I have two of those same mass, same speeds, but opposite directions, I have a positive momentum and a negative momentum. Overall, the system is zero momentum. You're like, well, wait a minute, how can that be? I have things moving. Yeah, you do, but if I use the blue and the red card as the system, if I have a plus 10 momentum coming this way and a negative 10 momentum this way, before they hit, the total momentum is 0. And that means after the collision, they have to take off at the same speeds, after the same mass, because the total momentum of the system, again, must be 0. Now, if you're different speeds or different masses, well, things get a little difficult and you have to use your head and or calculate. If I make this one a heavy and this one the light one, but I bring this one with a very heavy, fast speed and this one with a low speed, you know, things happen. If I bring in this one with a heavy, high speed and this one with a low speed, things happen. And so you want to ask yourself, well, why is that? What's going on there? Now, that's when we have energy conserved. It's a little different when we don't have energy conserved during the collision. Now, when energy is not conserved during a collision, it's called an inelastic collision, which is most real-world collisions inelastic. But there's a special inelastic collision when the objects stick together and move together after the collision. That's called a perfectly inelastic collision. Because when the objects come together and crunch and bang together and deform and make themselves stick together, that takes energy, and that's robbed from the motion of the system. Though that energy is robbed from the system, the momentum is not. So even though in a collision you can lose energy, you will not lose momentum, again, so long as you remove outside forces like friction sliding across the ground or other situations like that. So if I have a cart, another cart, again, same mass, and they hit each other, and this one comes in with a momentum, m times v, and they hit each other and they stick together, and there's some friction in these, but please ignore that. Immediately after they take off, if this came in with m times v, and then the mass doubled, if the mass doubled, then this initial takeoff speed should be half of the initial velocity, because you doubled the mass, because they stuck together. And that's a perfectly inelastic collision. Yeah, I know it lost speed as it traveled because there's some friction in one cart, but you're going to look at collisions, we're going to analyze collisions, the instant before they hit, the instant before the objects hit, and the instant afterwards. And yes, after that instant afterwards, after that initial takeoff, there could be other things happening and friction could take over and so forth. But when you analyze a collision, you're only analyzing a very small window of time. You're ignoring a lot of what happened before the objects connected, and you're ignoring a lot of the time right after the object connected. Also, to show you that, I'm going to take both of these objects and I'm going to bring them together roughly at the same speed. I'm going to try. And again, the total momentum of the system is 0 if I have same mass and same speeds coming at each other. One's a positive speed, one's a negative speed. If the total momentum is 0 before they collide, well then after they collide, if I do this right, I didn't do it right, let's see if I can do it right, they pretty much stop. Because they collided together, they stuck together, the overall momentum beforehand was 0, so the overall momentum of the system afterwards must also still be 0. So, I hope this gives you a physical sense of what's going on, because you're going to have to kind of apply these kinds of things and motions and such when you're doing problems, so hopefully this will allow you to visualize that. Okay? All right. There's going to be some follow-up questions perhaps. So we'll get to those, and thank you. Okay, so I almost forgot to show you one more set of examples of a system where momentum is conserved. We get so caught up in physics class in things, crashing together, and showing you that the momentum of that system always stays constant no matter how they crash together. But really, any system that is defined as, a set amount of objects, and as long as there's no outside forces acting on those set amount of objects, momentum in that system must always be conserved. They call this a closed, isolated system, where you have, 2 items and no outside forces, or 3 items and no outside forces. As long as those forces are internal within that system, momentum should remain conserved. To show you that, the other example I didn't get to show you is what we call a quote-unquote explosion. Right? So here I have 2 objects. I have my 2 carts. No momentum right now. They're both not moving. And nothing's going to happen right now. Well, if I take those 2 non-moving objects and I squish them together with this spring here. So I'm squishing them together. Now we have internal energy. Now that internal energy could be released, but right now, not moving, no momentum. Once I release these carts, they take off. But remember, if there's no friction involved and no other external forces, yes, there was an internal force, but no external forces, momentum must be conserved. And so, if you had 0 momentum in the beginning, you must have 0 momentum after they separate. And you do. But I know they're moving. But realize again, if one is moving one way, positive momentum, and the other is moving the other way, negative momentum, those 2 momenta must be equal but opposite. They must cancel. And in this particular case, if the masses are the same, not only are the momenta the same, but also the speeds are respectively the same. Now, in this particular case, energy is definitely not, quote unquote conserved, at least kinetic energy isn't, right? Because we had no kinetic energy in the beginning, and in the end, we have kinetic energies. And they don't cancel each other out because they're opposite directions. Remember, kinetic energy, you have it or you don't. That kinetic energy obviously came from the internal energy of the system, so we can at least say that. If masses are not equal, if I make one heavier, one lighter, if I release these, we would expect that the lighter one will go. What do you think? Let's find out. The lighter one goes faster, because that's got to make up the momentum. The lighter one's got to go faster to make up for the fact the heavier one's going to go slower, because m times v has to equal m times v. So that's explosions. Okay? All right, like I said at the end of the last segment, we're going to have some follow-up with this. So check that out, and thank you for watching.